All right, so we're talking about a specific type of word problem that you use derivatives for today. It's a pretty common one, so you'll see at least a couple of these, maybe one or two of them on your AP test. They're pretty common. We're going to learn about these things called related rate problems. First of all, I need to know what that is, and then how to solve them. I'd like to get through the sides of a right triangle today, so we're going to continue this chat about these up into tomorrow. So first of all, let's review a couple of things. Whether or not you write this is up to you. Do you remember how to find the derivative of an implicit function? Well, when you have an implicit function, that means that your y variable is a part of the function itself. It's not like y equals or something like that. Now, something else we talked about was, actually this is a little bit deeper than that. When we did these, we found the derivative of x we found the derivative of this thing with respect to x. So when you take the derivative of anything that just has an x, you do the derivative like normal. But when you take the derivative of anything with a y, after you take the derivative of it, you multiply it by a y prime. Remember that? And then over here, this would be 0. Okay, but that's not quite what this problem is either. You guys notice the bottom here? I'm finding the derivative of these things with respect to t. Now, let's say that x itself is a function of t and y is a function of t. Okay? So that means that when you take the derivative of this, you're going to do 2x and you get an x prime. Okay? Because the bottom doesn't match this, and this is a function of t. So it's really an implicit, instead of thinking that as x squared, you guys can think of it as x of t squared. So you guys see how that's a chain rule? You have the inside function as x of t, and you have the outside function, which is a square. So you put the 2 on the front, take 1 away from there, multiply it by the derivative of the inside. Okay, now a shorter way of writing this is not having the t in there. So if you take that out, x squared, right? 2x, x prime. So whenever you're taking the derivative of a variable that is a function of another variable with respect to that one, then it's a chain rule. So you get a prime factor on there. Okay. Now the short way I said it earlier is that basically when these don't match, you get a prime. Okay. So here's another one. So if y is also a function of t, then you get 2y, y prime. Okay. So, but that's implicit differentiation. So, any questions about that? No? Okay, so that's one review topic. We're going to be using that today. KMOS. Got to remember what this stuff means. What does this mean? This means this is the derivative of s with respect to t. Okay, and what that means is the rate of change of s with respect to t. The rate of change of s with respect to t. Okay, and in other words, we could say how fast s is changing as t is changing. That's what that means. Okay, the next one is the rate of change of y with respect to x. In other words, how fast is y changing as x is changing. Last one, rate of change of a with respect to p means how fast a is changing as p is changing. So that's something we'll want to be aware of today. Matter of fact, if I were to go back to this last slide over here where I was at, remember what I got here? We got 2x, x prime, plus 2y, y prime equals 0, right? Well, hello. I'm using the lazy man's way of writing a derivative, but what's another way I could write x prime there? It's really the derivative of x with respect to t. So how would I write that? dx over dt. How about this one? Instead of writing y prime, there you go. So that's that. Other things to be aware of here is units. You guys know, like, let's just say length is centimeters, right? Yeah, what would area be?
Centimeters.
Yeah, square centimeters, right? You measure area in square units. How about volume? Cubic centimeters, right? Velocity. You guys remember that's distance over time, so like something like centimeters over seconds, for instance. What would the acceleration be? Centimeters per second squared, right? So we're going to be using a lot of units today, and you want to know how to, if you didn't know any of these, you might want to jot them down. Should be aware of these. We've been talking about those for the past few days, but I don't know, maybe area and volume a little bit weird to you, but there you go. So those are some review things you got to make sure you're aware of before we begin the lesson. So you don't need to write this. I just want you guys to pay attention. But say you throw a pebble into a pond and it creates these ripples, right? Which is really just 4 separate circles, right? So let's say that the first radius, like right after you throw the pebble in, was 1. Let's say the next radius was 2. The next radius was 3, 4, and 5. So the radius is going up 1 every time we go up. And let's say that happens every second. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So after 1 second, let's say the radius is 1. After 2 seconds, the radius is 2. And after 3 seconds, the radius is, and so on, right? Now, I'm going to ask you guys a question. What's dr dt? Yeah? So the rate of change of the radius with respect to time. In other words, how fast is the radius changing over time? 1. It's going up 1. I didn't give you any units. Let's just say it's feet. Let's say feet. Let's say it's 1 foot per what? For every second, right? For every second goes by, the radius goes up 1. So the dr dt, the rate of change of your radius with respect to time, is 1 foot per second. Now, I've never asked you guys to find a rate that way, but I'm just asking based on what you understand about rates. Well, rates tells you basically how fast something's happening. And what's happening here is dr dt, how fast the radius is changing over time, is 1 foot per second. And you can tell that by just looking at the table, right? But let's go ahead and take a look at the area now. Now, the area is pi r squared. That's how you find the area of a circle, right? So what would the area of the first little circle be? No. It would be pi. Because if you plug in 1, 1 squared is 1, and 1 times pi is pi. What's the next area going to be? 4 pi. What's the next area going to be? 9 pi. Okay, now let me ask you another question. What is the rate of change of the area with respect to time. Any thoughts? So in English, how fast is the area changing over time? No. So like, how far apart is this? It went up by 3 pi, right? So from 1 second to 2 seconds, the area increased by 3 pi. So from here to here, dAdt is 3 pi. How about from here to here, what's the dAdt? 5 pi. It's going up by 5 pi. How about from here to here? I think that's 7 pi. What do you guys notice about dAdt? It's not the same, is it? It's getting bigger and bigger every time. So in other words, the rate at which the area is changing is not constant. It's always changing. The rate is, what do we call a rate that's increasing? Yes. Acceleration, maybe? Okay. All right. Well, anyway. So there you guys have it. We have, over time, we have 2 different variables that are changing. And actually, you can find more, but I'm just looking at 2 here. In this particular story problem, over time, 2 things are happening in this story problem giving you. The radius is changing and so is the area. And both of those have a rate. Now, our goal for today is going to be to realize that there's a relationship between those rates. The rate at which the radius is changing, don't you guys agree the rate at which this is changing affects the rate at which this is changing? Because doesn't the radius depend on the area? I'm sorry, the area depends on the radius? So if the radius is changing, then the area is changing. And so those 2 rates are related to each other, so we call these related rates. In other words, it's possible that one variable which is changing causes another variable to change at a certain pace as well. Okay? So that's what we call a related rate question. All right, so here's our essential question for the day. What is a related rate problem and how can we solve it? That's the goal. What are related rates? Related rates are 2 rates that are somehow mathematically related to each other. 2 speeds, 2 rates that are both changing together. It doesn't mean they're changing at the same pace. It just means that as this one is changing, the other one is changing with it. Okay, so in this, back to our rock in the pond story, the radius's rate affects the area's rate. Okay. What is a related rate problem? A related rate problem is a problem containing 2 related rates in which you'll be given one of the rates and your job is to find the other one. Okay, so if I give you the rate of change of the radius, you should be able to find the rate of change of the area, for instance. So it's a word problem where you have 2 rates and you use one rate to find another rate. Okay, we're going to use these 6 steps both today and tomorrow. Some of these steps are easy, some of them are hard. Sometimes this is hard, drawing the picture. And sometimes you actually don't even need to do it. This is easy. That should be okay. This should be pretty easy. This can be hard. Finding the formula. Now I'm going to give you a list of formulas to choose from today, but the problem is that's not an exhaustive list. There could be other formulas you could possibly use, and basically why that's hard is because it really depends on your prior math knowledge. Do you know how to find things? Can you, if I were to ask you, Dave, find the missing side of a right triangle, would you be able to do that? If not, then you're going to be really dependent on the list of formulas I give you. And you might have some trouble with like creativity and finding formulas. So that, I would say that's probably the hardest part, just remembering what math to pull in. This is easy. I think you guys will be okay with that. The last step can be a little bit tricky, but that's it. So basically, these are the steps we're going to go through, but there's two pretty tricky steps. Drawing, which is but formulas are definitely hard. The rest is pretty chill, but there's a lot of steps here, okay? And I think that's what ultimately makes it hard, the fact that there's so many steps to these problems. Let's go ahead and see what we can pull off, though. Word problems are always fun. Here's a list of some common formulas. Like, you're going to probably see problems that use areas, the area of a circle. In this case, we're showing that A and R are related to each other. Volume of a sphere, volume and radius are related to each other. The volume of a cone has three variables. Volume, height, and radius are related to each other. Sides of a right triangle, the Pythagorean's theorem, where these two are the legs and this is the hypotenuse. And then SOHCAHTOA will probably make an appearance tomorrow. Okay, so those are some common formulas we're going to be using. So let's go ahead and do our first problem here. So, hey man,
Mr. Bailey.
All right. That was surprising.
I'm like, wait a minute. He wasn't talking. He comes in. He's like, Mr. Bailey, a head full of hair. Yeah, I'm like, wait, we're doing math here.
No, that's cool. He's welcome to. He's a homie. All right. So, we're going to go back to the problem that I gave you guys earlier. But we're gonna hit it up in the more traditional way of doing it now, how we're going to be handling these problems. So a pebble is thrown into a calm pond and ripples form concentric circles. If the radius of the circles is increasing at 2 feet per second, how fast is the area changing at the moment when the area is 25 pi feet squared? Now, notice something. I have to ask you at a specific moment how fast is the area changing? Because remember how the area's rate was not always the same? So I have to ask you at this moment, how fast was the area changing? So, the first thing I told you guys to do is to draw a picture. So let's do that. So we have a picture of a circle here, right? And what we're going to do is anything that's changing, we're going to put a letter on it. So my radius is changing, so I'm going to put an R there. Okay? And that's pretty much all we need to draw for that one. And that might seem kind of stupid, and maybe you don't even want to do it in the future for these types of questions, but trust me, drawing comes in pretty handy on quite a few of these problems. So that's step one, is to draw a picture. Step two, what is step two? Identify the given rate, correct? Is that right? Okay. So in the problem, I told you they're going to give you one rate and they're going to ask you to find another rate. So a pebble is thrown to a calm pond and ripples form concentric circles. If the radius of the circle is increasing at 2 feet per second, go ahead and underline that. That is our given rate. Okay? Now, it's the rate of change of what? What is it talking about is changing here? It says the radius is changing, and this is over time. So the rate of change of the radius with respect to time is 2 feet per second. So that's my given rate. They gave me the rate of change of the radius with respect to time is 2 feet per second. Now I'm going to put a plus in the front. Do you guys know why I'm putting a plus there? It's increasing. The radius is getting bigger. Be aware of that. You're going to have problems when you talk about something decreasing. You're going to need to put a negative there. Okay? So be aware of that. Number 3. Identify the rate we want to find. I'll call it the desired rate. Identify the desired rate. What rate are they asking me to find? The area. See right here it says, how fast is the area changing? So they want me to find, how do I write that symbolically? D, dA, dt. You could do dr, but we're not doing that. It's dt. We're going to do dt. And there you go. Now, we don't know what this is yet. We're trying to find that. But a good thing to do might be to think about what units you want to use. Okay, so what are my units going to be for this thing? Well, area is measured in squares, so it's square feet. If radius is feet, then area is square feet, and time is still going to be seconds. So we want the units are going to be square feet per second. All right. What does step 4 say? Formula. Now, we're starting easy. We're working our way up to harder things. What you want to find is you guys want to find a formula that connects these two variables, r and a. Look at your formula list that I gave you. What formula connects the area with the radius? The circle area, which is what? A equals pi r squared. Got to have both variables in there, but yes, A equals pi r squared. This is all just setup stuff. All right, so I've got a picture. I found the rate that they give me. I have the rate that I want to find, and now I've got a formula that connects those variables, that relates those two variables. But I don't want to find out how area relates to radius. I want to find how the rate of change of area relates to the rate of change of radius. So that's why we do step 5. What is step 5? Differentiate this thing. So we're going to do d over dt. It's always with respect to time when you're doing related rate questions. All right. So I want to find the derivative of this formula with respect to time, so that instead of finding the relationship between area and radius, I'm finding the relationship between their rates. So here we go. If I apply the derivative here, I just get dA dt. Over here, pi is a constant, so that just stays there. What's the derivative of r squared? 2r. I'm going to put the 2 in the front. But does the t match the r? So what do I need here? R prime, but I'm going to write what instead of r prime? So now I have a formula that shows the relationship not between a and r, but the relationship between dA dt and dr dt. Okay, so what does step 6 say? Plug some stuff in. Plug in whatever you can. Now, do I know dr dt? What is it? Dr dt is 2, right? R. We'll have to come back to that one. dA dt, we don't know that either. But that's what I'm trying to find, so we know that that's got to stay like this. Okay, so we know we're not going to have that. But I need R. Does anybody know what R would be? Well, let's read our problem again. A pebble is thrown into a calm pond and the ripples form concentric circles. If the radius of the circles are increasing at 2 feet per second, that's this. How fast is the area changing when the area is 25 pi? Do you know what the R would be? 5. Maybe 5. So check this out. Sometimes you can't. You guys agree you can't find dA dt until you have R and dr dt, right? We've got dr dt. So sometimes if you have one more missing variable, you got to come back to this thing over here. Sometimes they'll just tell you, like instead of me saying find it when the area is this, I might have just told you find the rate when the radius is something. That would be easier because then you can just plug it right in. But sometimes they give you something else. So you got to come back to this guy and plug it in. I know my area is this, right? So we divide both sides by pi, take the square root, radius is 5. Okay? Okay, so dA dt is equal to 2 times 5 times 2 would be 20, right? 20 pi. And what are my units? Square feet per second. So what this means then is, we threw a rock in a pond. The radius is growing at a steady rate of 2 feet every second. But the area, at the moment when it's 25 pi, the area is changing at a rate of 20 pi feet per second. Square feet per second. Okay? So a lot of steps there. The first 3 steps are just to orientate yourself. You know, figure out, where am I in this problem? What is it looking for? What do I have? Steps 4 through 5 is where the real stuff happens. Find the formula that connects those variables, take the derivative, plug it in, and solve for what you can. Okay, so there's that. We're gonna do a lot of these in the next few days, so hopefully it'll get a little bit easier as we go. Let's go ahead and write down, or let's find this problem. All right, so a balloon in the shape of a sphere is deflating. If the radius is decreasing at a constant rate of 3 inches per minute, how fast is the volume decreasing when the radius is 2 inches? Okay, so I'm just going to draw a circle again because I can't draw a sphere on a piece of paper, but it's going to look like that. All right, but I want you guys to do step 2. I want you guys to identify what rate are we trying to, or what rate did they give us? All right, so what do you think, Viv? Did you find your given rate? Very good. -3. She remembered the negative because it's decreasing. Now, how about the symbols though? D something, D something. What would we put there? Yeah, we're talking about the rate of change of the radius with respect to time. All right, number 3. Go ahead and see if you guys can do the next thing. I would also like you to include units. Okay. That's good. dV, dt. So when you say you didn't finish, you didn't get the units yet. Okay, that's all right. Somebody want to tell me what they think the units may be? Yeah?
Inches cubed over.
Very good. Cubic inches per minute. Does anybody have any questions about either of these so far? Let me know if you have a question. It's cubed because it's volume. Volume is cubed. Yeah. And we have volume because it's a sphere, right? But now I could have changed this problem. For instance, I could have given you guys the rate of change of v with respect to t. Like I could have told you that how fast the volume's changing, and then I could ask you to find dr dt instead. So just got to pay attention to which one you're given, which one you want. But yes, anytime you use volume, it's going to be cubic. All right. Now I want you guys to do step 4. Step 4 is to find a formula that connects. What 2 variables do I want to connect? Radius and volume. I want to find a formula that connects radius and volume. Go ahead and see if you can do that. You got a little list of formulas there. What do you think, Thea? Cool. There we go. That connects volume and radius, right? All right, step 5. Let's differentiate that. Right? That's where you take the derivative of this thing with respect to time. Yeah. Okay. What? Go ahead and tell me what you got.
Okay, so I put dv
Good so far.
equals 4 pi r squared.
That's right. Now you're missing one.
Dr.
There you go. Nailed it. You weren't wrong at all. So first of all, we changed v to dv dt when we do that. Over here, when you take the derivative of r cubed, the r goes to the front, the 3 goes to the front, which cancels the 3 on the bottom, so you're just left with 4. You take 1 away from your power, so it's r squared, and then you multiply it by dr dt. Okay? All right, step 6, we just plug in and solve. So, on this problem, you're given some stuff. We want to find out what this is, right? dv dt, that's what the question's asking for. Find the rate of change of the volume. So we need a radius and we need dr dt. And we have both of those things. So see if you guys can find them. And plug it in and see what you get. All right, so there's that. Okay? Oh, question?
Wasn't it per minute?
Was it minutes, guys? It was. Who was that? Vivian? I owe you guys some points. I'll get you guys some points. So it was per minute. It was not per second. Okay. I had a student practice here, but I think I'm going to bypass it. I'm going to move on to this. I want you guys to I want you to read this and try to turn it into a picture for me real quick. Okay? So we have a 25-foot ladder that's leaning against a wall. So here's the wall. Here's my ladder. And it's 25 feet. Now, is the length of my ladder ever going to change? No. So I'm going to put a number there. If you have something that can change, you put a variable, okay? But if there's a number that doesn't change, put 25. Okay. Now they tell us that the base of the ladder, which we'll call, if the base of the ladder is being pulled away from the wall at a rate of 2 feet per minute. So here's my base. We're pulling the ladder away from the wall. What happens to the height as you do that? It's going to go down, right? So as the base increases, the height decreases. Are those two rates going to be related to each other? Yes, they will. Okay, so if the base of the ladder is being pulled away from the wall at a rate of 2 feet per minute, now would you guys say that well, we'll get to that in a minute. How fast is the top of the ladder moving up and down the wall at the instant when the bottom of the ladder is 24 feet away from the wall? Now they say that the bottom is 24, right? But I'm not going to write 24 here. Why? Because it's changing. I want to find how fast is the height changing when this is 24, but still it's changing. So but the ladder length never changes. So I'm going to leave that as 25. So on your pictures, constants go, but variables stay as variables. Okay, let's go ahead and do step 2. What rate did they give me? 2 feet per minute. What? We'll call this A, we'll call this B. This is D what, D what? So it's not dA. If the base of the ladder is being pulled away from the wall at a rate of 2 feet per minute, is dB dt. The base is increasing, right? So it's dB dt. Now, is it going to be a positive or a negative? Well, it's positive. Why? Because we're pulling the base of the ladder away from the wall. What's happening to it? It's getting bigger. So, yeah, so dB dt is positive, okay? It's positive what? Okay. What rate am I trying to find? We want to find how fast is the top of the ladder moving down. That's A, right? So we're looking for dA dt. What are my units? What are my units going to be? Just feet per minute, right? It's not, we're not doing volume here, it's just a length. So basically, as the base of the ladder, if the length between the base...
feet per second.
Blasted. Thank you. All right. So, and we would expect this to come out to be positive or negative?
Negative.
Negative, because as B gets pulled further and further away, that top slides down, doesn't it? And so you would expect A to be shrinking. In other words, negative rate. Okay. What formula can you guys think of that would connect A and B together? It's Pythagorean's theorem. Good. So, here we go. Formula is A squared plus B squared equals C squared. All right. Let's find our derivative. So if I took that formula and I did the derivative of it with respect to time, what would this become? 2a times a prime, but I'm going to write plus
2b b b
good. Now what rate am I trying to find here, you guys? A dA dt. So I need three things to solve this problem. What three things do I need to find dA dt? Need A, B. Okay, so which ones do we have already? We have dB dt. What is it? It's 2. What else do I have? Oops. Okay. What is B if we have it? There you go. Right there. There's your B value, 24 feet. That's how far away it is from the wall at that point. Which one do I not have then? How am I going to find the A? Because I need this before I can begin finding this. Any thoughts? The formula. Come back to this over here. If you need, we need to find. Sometimes you don't have one of them. So when you don't have one of the things you need, you come back to step 4. Can we solve for A now?
Yeah.
Yes, we can. All right, so let's do it. Thank you. I didn't know what that was. 49?
7.
Okay, so now we're ready to plug in. I know what A is, I know what B is, and I know what dB dt is. So let's plug it in and solve. Okay, so we have 14 dA dt plus 96. Anybody got a calculator? Want to help me with what negative 96 over 14 is? 6.1? 6.8? And that was in what per what? Per minute? I can't imagine somebody sitting there pulling the base of a ladder away from a wall at 2 feet every minute. Some people got nothing but time on their hands. This is how fast the height is changing at that moment, okay? At that moment, that's how fast the height is changing.
It's gonna be a couple of minutes.
So, guys, let me ask you a question. You ready? So when you get down here and you take the derivative and you check to see what do I need to plug in,
Yeah.
and you find there's one thing you don't have, what do you always go back to?
Step 4.
Step 4. Go back to step 4 to find that missing piece, okay? That's your big takeaway from that one. All right, so I want you guys to try one of these real quick. I don't want to give you one that's too hard. That one's too hard. That one's too hard.
5 minutes.
Do I really?
Yeah.
Okay.
Okay, time's up.
I didn't say time was up. You guys gonna really pack up? Buttholes. All right. Try student practice 2 here.
All these guys are like,